Warning: in this video we generate toxic gases. This experiment must be performed outside or in a fume hood. We also use corrosive acids. Wear gloves when handling them. Greetings fellow nerds. In this video we're going to make glow-in-the-dark powder. Glow-in-the-dark substances are materials that absorb light energy and then release it slowly over time as a visible glow. This process is known as phosphorescence. You've probably already seen these a lot in children's toys, stickers, as well as emergency equipment and signage. When exposed to light, the material's atoms absorb the energy, exciting their electrons. These electrons become trapped in a higher energy state, and when they eventually return to their original state, they release the stored energy as light, causing the material to glow in the dark. There are actually a lot of substances known to science that do this, but the two most well-known ones to the public are zinc sulfide and strontium aluminate. Strontium aluminate is the more modern one and provides the longest and more intense glow, so we'll try and make that in this video. Most of you probably don't remember this or even know that it happened, but 15 years ago when I first started this YouTube channel in 2009, the first mega project was making glow-in-the-dark powder. By today's standards, that video kinda sucked. So I'm going to revisit that video with my modern and experienced video presentation style and hopefully give it the attention it deserved. Before we begin, here are the precursors to glow-in-the-dark powder. If you already have them, then you can skip ahead to where we mix them. Otherwise, we're going to spend most of this video making them ourselves. There are two critical elements though that you'll need to acquire, and they are Europium and dysprosium. These are dopants for our glow-in-the-dark powder and critical for them to work. Fortunately, in today's modern e-commerce utopia with worldwide shipping, you can easily find online sources of these elements. We're only going to need about 1 gram each, so look for those before considering this experiment. I got mine from a company called Stanford Advanced Materials. You can also get these elements from AliExpress and eBay, but they're not nearly as trustworthy. Before we begin, we're going to need lots of nitric acid. I already have several videos on making nitric acid, so I won't go into detail here. But briefly, we mix calcium nitrate fertilizer with sodium bisulfate and then distill off the nitric acid. Then the nitric acid is purified by azeotropic distillation to get concentrated 68% nitric acid. Once we have our nitric acid, we can start work on making our precursors. The first precursor is aluminum nitrate. Theoretically, the simplest way would be to react aluminum metal with nitric acid. But in practice, the aluminum passivates when exposed to concentrated nitric acid and doesn't dissolve. And even with dilute nitric acid, it may still resist dissolving if the aluminum metal was already passivated, like say at the factory where it was made. So we're going to need to use a roundabout method where we use hydrochloric acid to dissolve it first. First, we start with 400 milliliters of water and add to it 100 milliliters of 30% hydrochloric acid. Then we add 33 grams of aluminum foil. Stir it for about an hour or so and it will react and dissolve, producing aluminum chloride and hydrogen gas. At least this is the formal equation we would probably put in textbooks. In actuality, it's a little more complicated as it produces an aluminum hexaqua complex. And that in turn reacts with a little extra aluminum to dissolve a little more than stoichiometry would dictate. But we'll just use the formal equation to keep things simple, as we're not going to be doing any complex chemistry that requires the correct equation. Anyway, hydrochloric acid is used because it breaks the aluminum oxide passivation layer and thus will dissolve aluminum metal. Eventually, the dissolving aluminum will neutralize the hydrochloric acid and the reaction will stop bubbling. For our reaction, we're using a deficit of hydrochloric acid to aluminum, so it won't completely dissolve. But we don't need it to, as we now add in 50 milliliters of concentrated 68% azeotropic nitric acid. The exact concentration is not too critical. We're making the solution acidic again and dissolving more of the aluminum metal. At this point, we're making aluminum nitrate, which is also mixed in with aluminum chloride from earlier. After about half an hour, the reaction will calm down again and we add in a further 70 milliliters of 68% nitric acid. The dramatic change in color is happening from the excess nitric acid reacting with hydrochloric acid to form chlorine gas and various nitrogen oxides. Anyway, at this point, on top of the beaker, we put a large round bottom flask of cold water to serve as a condenser for refluxing. We turn on heating and let the reaction simmer for 30 minutes. Eventually, all the aluminum metal dissolves. Now we add in 140 milliliters of 68% nitric acid and gently boil the reaction. What we're doing now is converting the aluminum chloride into aluminum nitrate by exploiting the previous reaction to destroy the chlorides. We need to do this as we can't have chloride ions in our product. We didn't add all the acids at once because the aluminum metal tends to produce a tremendous amount of heat when dissolving in acid, and the reaction can boil over. So that's why we added the acid in stages. Anyway, we can tell the reaction is moving forward by the yellow-brown haze of nitrogen dioxide and chlorine gas that forms in the beaker from the decomposing aluminum chloride. At least that's what should be happening. I've been boiling for an hour and I don't see any nitrogen dioxide yet. Let me add in another 100 milliliters of nitric acid. There we go, that is what we want to see. Now we let it boil for several hours to drive the reaction forward and destroy all the aluminum chloride. We'll know when it's done when the haze clarifies. And it looks like we're there, but it might have just run out of acid. So I'm going to add in 100 milliliters of water to keep it dissolved and 50 milliliters of nitric acid to ensure all the chlorides were destroyed. We bring the heating back up to boiling and it looks like there is indeed no more haze, and thus we can be sure all the chlorides have been destroyed. As we're boiling and we know we have excess nitric acid. We now have relatively pure aluminum nitrate, but we need it ultra pure, so we're going to recrystallize it. Turn off the heating and let it cool until it stops boiling. Then check the volume, and if the level is less than 500 milliliters, add in enough water to bring it back to 500 milliliters. If it's starting to crystallize like mine, then heat it back up until it's fully dissolved. Now we filter the hot solution to remove any insoluble impurities. While it's still hot, we pour it into a clean plastic bin for crystallization. Put a lid over it to protect it from dust. After a couple of hours, if it's still not crystallizing, it might need a seed crystal. Drop in a seed crystal of aluminum nitrate and let it sit for several hours to slowly crystallize out. You can get seed crystals from the original beaker we used to pour the hot solution. It will likely have dried and crystallized the residue by now. Anyway, after several hours, we can filter it. But for extra yield, I'm going to take the bin and chill it in the freezer to further crystallize it. And here we are after leaving it in the freezer overnight. Break up the crystals since they'll likely have solidified together. You might be asking why I didn't just let it crystallize in the beaker. I tried that in a previous run, but it just solidified in the beaker and was too hard to remove. So spreading it out in the bin was more effective as the crystals were smaller and easier to break up. Once all the crystals are broken up, we vacuum filter on a fitted funnel. Now since we froze the solution earlier and it's still cold, we cover it up and let it thaw back to room temperature before vacuum filtering again. A little of the solution will melt off as it returns to room temperature, and we don't want to thaw out in the final storage container and make a mess. There we go. Finally, we collect our purified aluminum nitrate nonahydrate. My yield was about 301 grams. The filtrate is water, nitric acid, as well as impure aluminum nitrate nonahydrate. You can save it and recover the nitric acid by adding sodium bisulfate and distilling off the nitric acid. You can calculate how much sodium bisulfate you'll need by subtracting the amount of purified aluminum nitrate nonahydrate you recovered from the theoretical amount you should have gotten. Now you might be wondering why I don't let the aluminum nitrate completely dry solid and get maximum yield. The reason why is because that actually gives a less pure product. When you crystallize a solution, the less soluble components crystallize out first. If they are in huge excess, then the impurities will stay in solution until they become saturated and start crystallizing out themselves. So if you stop the crystallization before that happens and filter off the supernatant containing the impurities, you can get a purer product than what you originally started with. You sacrifice yield for purity in that case. And that's why I don't let it dry completely and instead just filter it off. Okay, so we're done with the aluminum nitrate nonahydrate. Next, we're going to make highly purified calcium ammonium nitrate. This is sold as fertilizer, but is a little impure. To make our glow-in-the-dark powders, we'll need to purify it. We start with 600 grams of calcium ammonium nitrate fertilizer. We then add 200 milliliters of water and then gently heat until it dissolves. Now normally we would filter it, but when I tried, there was a very fine silt that passed right through. So to deal with that, we add in 5 grams of aluminum nitrate. This is the same aluminum nitrate we made earlier. You can even use the impure aluminum nitrate filtrate that we didn't crystallize. The aluminum nitrate behaves as a flocculating agent and makes the particles of silt stick together into larger clumps that can be filtered. Let it stir for several minutes and then let it settle for half an hour. The clumping can get so big that they scatter light and look like the solution is getting cloudier. Flocculation is a well-known process for clarifying solutions of pesky, hard-to-filter suspensions, although the usual flocculating agent is aluminum sulfate or alum. We can't use that here since we want the highest purity, so we're using aluminum nitrate. Anyway, now we filter it, and you can see the aggregated clumps. And there is the filtrate, crystal clear with only soluble impurities now. Now we pour it off into a beaker and drop in a seed crystal. I have crystals from previous runs. You can also drop in a single grain of the original fertilizer. The minuscule impurity is acceptable. Anyway, we now place the beaker in the freezer and let it cool overnight. And here we are the next day. The calcium ammonium nitrate has crystallized out and left the impurities in the supernatant. We now break up the crystals and suction filter them. Just like with aluminum nitrate, we cover the funnel so the moisture in the air doesn't condense, and let the crystals thaw back to room temperature. Then we suction filter again. Once it's reasonably dry, we transfer into a resealable airtight bag. Alternatively, you can also transfer into a jar if you want. And that is our high purity recrystallized calcium ammonium nitrate. Now we make strontium nitrate. Once again, it is possible to buy directly, but I didn't find all that many sources. Strontium carbonate seems to be easier to get, so we're going to use that as our precursor. First, we get 150 grams of strontium carbonate in a flask. Then we add in 100 milliliters of water. If you're looking for strontium carbonate, you can find it for pottery uses in making glazes. It's also available for making pyrotechnics. Anyway, once all the water is in, we set up a dripping funnel on top of the flask with 120 milliliters of concentrated azeotropic nitric acid. Make sure the funnel is open to air and that you're doing this outside in a fume hood. Now we slowly drip in the nitric acid and let it react with the strontium carbonate. The reaction will produce strontium nitrate and carbon dioxide gas, which will bubble out. We didn't just dump it in because the bubbling is quite vigorous and can easily bubble over, so we need to add it slowly. I said before you have to do this outside or in a fume hood because unless you're using highly pure strontium carbonate, this reaction will produce small amounts of toxic and repulsive smelling hydrogen sulfide. This might seem odd, but it has to do with how most strontium carbonate is made. The most common mineral of strontium is strontium sulfate. But this is insoluble in water, so to convert to the carbonate, the strontium sulfate is heated at high temperature with coal to produce strontium sulfide and carbon dioxide. This strontium sulfide is now water soluble and is precipitated with sodium carbonate or even carbon dioxide to make strontium carbonate. The problem is there is usually a few percent strontium sulfide contamination in the strontium carbonate. It's a tiny amount, but considering hydrogen sulfide is extremely repulsive to humans, you have to do this reaction in a fume hood. The nitric acid will liberate the hydrogen sulfide from the strontium sulfide. Anyway, add in all the acid and let it stir for half an hour. I deliberately use an excess of strontium carbonate so the solution remains alkaline and precipitates most metal impurities. If you accidentally use too much acid or a higher concentration and all the strontium carbonate dissolves, just add in small amounts of strontium carbonate until you get a milky solution like this. We want to be sure it's alkaline and the impurities are precipitated. After half an hour of stirring, we suction filtered the strontium nitrate with a fitted funnel. You may run into the problem where some of the insoluble material is so fine that it passes right through the filter, making it cloudy. We need crystal clear purity, so we're going to remove the final bit of contaminants by flocculation, just like we did with the calcium nitrate. We add in 5 grams of aluminum nitrate nonahydrate and stir for an hour. You can already see the yellow color of the impurities disappearing. The aluminum also reacts with any residual hydroxides and carbonates to form insoluble aluminum hydroxides and carbonates that precipitate out and also stick together. What we get is bigger aggregates of insoluble particles that are easier to filter. In fact, the mixture can actually get cloudier as the flocculant mass gets large enough and dense enough to see. Looks like we're done. Now we filter. I didn't add the aluminum nitrate at the beginning when we filtered the bulk strontium carbonate because we needed to remove most of the impurities first. Aluminum nitrate does have limits to how much it can flocculate. You might be wondering if the aluminum itself is now a major impurity. It is, but since we'll be adding it later as reagent, it doesn't matter for this particular case. Anyway, this time the filtrate is crystal clear. Now we crystallize the strontium nitrate. Unfortunately, we can't use the heating and cooling trick like we did with calcium nitrate and aluminum nitrate, as the solubility of strontium nitrate doesn't change all that much with temperature. So we're going to have to crystallize it the old-fashioned way by simply letting it evaporate. To help it along, I'm putting it in a plastic box with a small dehumidifier. This will dry the air inside of the box, and the covered box also helps keep the dust out. The drying box is optional, and you can just leave your strontium nitrate out if you want. Evaporate down until it looks like it's equal volume solid strontium nitrate and solution. This took me about a week. Now we break up the larger crystal chunks so we free any entrapped solution. Use a titanium, glass, or plastic rod or bar when doing this. Avoid steel or iron, as iron contamination will severely diminish the quality of our final experiment. Anyway, when it's all broken up into individual crystals, we filter. We don't need to thaw it this time since it's already at room temperature. And then we transfer it into a bag for storage. And there it is, a purified strontium nitrate. These crystals are rather large, so you may need to crush them into a powder for easier weighing and measurement. Now we need to make our dopants, europium nitrate and dysprosium nitrate. So here we have samples of europium metal and dysprosium metal. I have about 1 gram each. I got mine from Stanford Advanced Materials because I needed to ensure absolute purity, but you can also buy samples from online retailers like AliExpress and eBay. Europium is usually bright and shiny, but it's also air sensitive and corrodes very easily. A little air got into the vial during shipping, which is why this sample is dark and tarnished from europium oxides. Europium is actually used a lot for its optical properties in various phosphorescent and fluorescent materials. Over here we have dysprosium metal. It's much more resistant to air, so it still retains its shiny luster. Dysprosium has interesting magnetic properties when alloyed with other metals, and also has notable neutron absorption characteristics, so it has use in nuclear reactors. It's not often we get to see these metals in real life. I think more people have seen gold and silver than have seen these. So I'm just taking a minute to examine them before I dissolve them in acid. Before we begin, we weigh the vials we'll be storing our rare metal nitrate solutions in. This is so that we can calculate our concentrations later. Now we transfer the metal samples from the ampule into the vials and weigh them. This is so that we can find the precise mass of the metals, as we'll be needing high precision later. While I did order 1 gram, the actual mass can be off by several percent or even more for very small samples, so we need to weigh it ourselves. Be sure to keep track of what metal is in what vial. Now we get the vials onto the hot plate. You can already see the europium corroding now that it's exposed to air. Anyway, to each vial we add about 5 milliliters of water. The exact quantity doesn't matter. The dysprosium reacts extremely slowly with water, but the europium is very reactive. It produces europium hydroxide and hydrogen gas. Let it react on its own for several minutes until it calms down. Now we add in about 4 milliliters of azeotropic 68% nitric acid to each vial. The dysprosium reacts with the nitric acid to produce dysprosium nitrate and nitrogen dioxide gas. The europium hydroxide is reacting with the nitric acid to produce europium nitrate. And it's also reacting with leftover europium metal bits too. Like before, let it react with several minutes until it calms down. The reason why we didn't add the nitric acid directly is because the reaction is pretty vigorous and we don't want to accidentally boil over out of control. So we add the chemicals in stages. Now that's calmed down, we very gently raise the hot plate temperature to lightly boil the vials and drive the reaction forward. Once everything is dissolved, we turn off the power and let them cool. Now we weigh our vials and cap them off. By knowing the mass of the vials and the mass of the metals we started with, we can know the concentration of metal in solution. The amount of nitric acid is of little consequence, but we need to know the metal concentration so we can precisely add it later. And there are our vials of europium and dysprosium nitrate solutions. An interesting property of these metal ions is that they are fluorescent under ultraviolet light. especially the europium. It's pretty rare for an inorganic metal salt to be fluorescent like this, and this lets us know these samples are authentic. Anyway, we now have made all of the precursors needed for making glow-in-the-dark powder. We can finally begin. This is the formula we'll be using to make strontium aluminate doped with europium and dysprosium. For every 1 mole of strontium, we need 2 moles of aluminum. And then we need 1 mole percent of europium and 2 mole percent of dysprosium relative to strontium content. We'll also need 0.2 moles of boric acid as a flux. Now we're not going to make a full 1 mole of strontium aluminate, that's way too much for a microwave combustion process. And so we'll scale the formula down to 0.005 so we have a much more manageable quantity of chemicals. Now that we have our scaled formula, we can begin. On a precise milligram scale, we get a small mason jar or canning jar to serve as our container. I'm not using a beaker because at the temperature we're working with, there's a small chance it'll shatter, and these mason jars are very cheap as to be disposable. They're perfect for this sort of experimentation. Anyway, we're going to start with our rare earth metals first since they're the hardest to weigh. We have to add in 7.5 milligrams of europium metal. Obviously, this is extremely difficult to accurately measure out that quantity directly, but since we dissolved it into solution and we know the total mass of the solution, we can calculate the concentration of the solution. And using that concentration, we can divide the europium metal by it to find out how much solution we can substitute it for. And this quantity is much easier to weigh, and we can drop that in by pipette. Your numbers will likely be different depending on how much metal you actually have and the actual amount of water and acid you used. So you'll have to redo the calculation for your own numbers. But as you can see, it's not hard. Now we do the same for dysprosium. We need about 16 milligrams of metal, but a much easier to handle amount of solution. This is why I didn't bother to dry out the rare earth metal nitrates into solids. Although you may still prefer to dry it into a powder if you're more comfortable with handling that. Anyway, don't worry if you're off by a little bit. Drops of solution aren't very precise, but even if you're off by 20% or so, the glow-in-the-dark powder will still work. So now that we have our rare earth metal dopants, we tear the scale and now we add in 61 milligrams of boric acid. This will serve as a flux for the reaction. You don't need it to be super precise, and I still had great results even if I was off by 20 milligrams. Next, we add in 1.058 grams of strontium nitrate. Once again, you can be off by several percent. And then we add 3.75 grams of aluminum nitrate nonahydrate. Now the next step is to heat these chemicals up to a high enough temperature that they decompose into their oxides. And that's how we get our strontium aluminate. And in fact, another YouTuber, Apoptosis, has an excellent video doing exactly that and making strontium aluminate with a microwave kiln. I've linked their video in the description. But rather than use a kiln, I'm going to take advantage of the fact that we're using nitrates. Nitrates are oxidizers, and that conveniently means we can burn them with a fuel and get high temperatures relatively easily. This is why I use nitrates rather than cheaper chlorides or sulfate salts. Well, than the fact that chlorides and sulfates would interfere with the strontium aluminate anyway. Of course, now we need a fuel. The fuel of choice for this reaction is urea, but we need an extremely clean and pure source of it. And in true amateur chemist fashion, we'll be using diesel exhaust fluid as our urea source. It's cheap, readily available, and already comes dissolved in deionized water for us. All diesel exhaust fluid comes in a standard concentration of 32%, so your results should be consistent across batches. We add in 20 grams of diesel exhaust fluid to our metal nitrates and shake until dissolved. Now I'd like to say there was some deep theoretical calculation for that quantity, but really I found that quantity empirically. It can vary slightly with different microwaves, so you may need to run several experiments with slightly different quantities to find the best one for yours. Anyway, once it's all dissolved, we can get to combustion. Now we can't simply heat this on a hot plate. Trust me, I've tried. And a hot plate is not hot enough to ignite it. So we'll have to use a microwave. We put the jar in the microwave and we cover it with a watch glass, or in my case, a small round bottom flask. Then we set for 5 minutes and simply wait. At first, it will simply boil off the water. While it's doing that, I have to make it clear that you should use a microwave that you've designated for chemistry only and make sure it's never used for food again. You don't want toxic chemicals contaminating your food. Microwaves are cheaper than laboratory hot plates, so do not do this experiment if you can't get one. Additionally, this experiment must be performed outside in a fume hood. A lot of smoke and combustion products will be produced, and you can already see the smoke starting. Anyway, after the water is boiled off, the urea and nitrates will react and combust. What's happening is the urea is essentially burning while being oxidized by the nitrates, generating very high temperatures. The metal oxides produced then crystallize into strontium aluminate. The dopants of europium and dysprosium incorporate into the structure and replace some of the sites of strontium. Anyway, when the combustion occurs, you'll see it as a flash. When that happens, the reaction is complete and you can stop the microwave and open it. It's very hot, so use some tongs. Take it out and place it on a block of wood to cool and remove the lid so any excess moisture can evaporate away. The wood block helps it cool slowly since it's an insulator and will reduce the thermal shock that can lead to the jar cracking or shattering. When it cools, get an ultraviolet light. I prefer using these UV LED flashlights. They're easy to get off Amazon or AliExpress. And just shine it onto the strontium aluminate. You can see even with the lights on, there is a visible green tint. Let me turn off the lights. And let me hit it with the UV again, and there we go. That is amazing. Amateur-produced phosphorescent powder made with fertilizers, foil, pottery materials, and diesel exhaust fluid. Now granted, this synthesis is rather sensitive. If you're having problems, there are a few things to try. If the mixture just isn't igniting even after several minutes of microwaving, check if it's boiling and burning. If it is, then you may need to scale down and use less mixture overall so it boils faster and ignites. But if it seems to get wetter as you scale down, then maybe you need to scale it up so there's more of a microwave target to heat up. If it ignited but is still mostly brownish or yellowish unreacted urea and doesn't glow, then you need to use less urea. Too much urea with too little oxidizer won't completely burn. Try removing 1 gram of urea at a time from the recipe and try again. If it did ignite and doesn't glow, but the product looks correct, being a white solid, then you may need to increase the urea content. To understand why, if you were paying attention to the stoichiometry, you might have realized I still used way too much urea. We should not need this much urea to burn this amount of nitrates. The reason why I found 20 grams to be optimal is because my diesel exhaust fluid likely decomposed a little during storage, so I needed a little more to compensate. But another important reason we needed so much is because the europium needed to be reduced from the 3+ to the 2+ oxidation state. Europium nitrate is in the 3+ oxidation state, but europium 3+ does not exhibit adequate glow in this particular material. This is why I said earlier if your samples combusted properly and gave a proper looking product but didn't glow, you should add more urea. It's actually full of europium 3+. We need the combustion to produce the reducing conditions necessary to have europium in the 2+ oxidation state. Now if it worked out and if it's glowing correctly but just seems really weak or spotty, you may need to adjust the boric acid content. Too little or too much will reduce glow. I tried a lot of different amounts for my runs before settling on the mixture in this video, but my friends who have tried this say they had slightly different ideal recipes. At this point you might be asking, what is the mechanism of the glow? What's happening is the strontium aluminate absorbs ultraviolet light and excites the electrons from the valence band of the crystal to the conduction band. Some of these electrons get trapped by europium and eventually they relax and emit light. This takes several seconds and is the basis of phosphorescence in this material. But to make it last longer, like minutes or even hours, another trap can be introduced like dysprosium, which traps electrons as they exit the conduction band. These electrons eventually escape from the trap back into the conduction band where they can find europium and eventually emit light. This reservoir of excited electrons can last minutes to hours, and allows us to substantially lengthen the afterglow time. And that's how this phosphor works. Now knowing this, we can start experimenting with our parameters and exploring the science. I said that the dysprosium traps the electrons and increases glow time. So what happens if we make a sample with no dysprosium dopant, just europium? I have it here beside my best sample. Let me hit it with the ultraviolet light. And here it is. You can see it decays much faster than with dysprosium, showing that dysprosium is needed to make it last longer. Of course, this leads to the question, if a little dopant works, can we increase the amount of dopant and get a supercharged glow that lasts even longer? Here's a sample I made with 3% europium and 5% dysprosium. And while it does work, it's not brighter and also decays faster than the best sample. What's happening is the excessive amount of dopants causes them to interfere with each other and quench the effect. So that's why you need to find just the right amount for maximum glow. Now, I said earlier that defects in the crystal lattice can also serve as sites for excitation and trapping. It's a weak effect, but we can see it if we make a sample without any dopants. Just strontium and aluminum, along with boric acid and urea as usual. It's extremely weak. I had to turn my camera exposure on maximum to see it. But it's definitely there as a brief white afterglow. It's not a residual glow from my flashlight since I'm deliberately aiming the flashlight away from the sample. It's white because the defects in the crystal are completely random and so they have random energies, and thus emit in a broad range of light. An interesting side note is that a lot of regular materials and minerals will do this, but the effect is so tiny that you need extremely sensitive equipment to detect it. Anyway, so there you go. Even if you can't get the rare earth dopants, you can still do this experiment and notice a tiny effect, albeit a very weak one. You probably have better results from peanut butter. But anyway, if this works with no dopants, and we've already established dysprosium helps extend the lifetime, would dysprosium do that here? I made a sample without europium and with just dysprosium this time. The reason why I'm looking at the top is because the sample exploded during heating and splattered across the top. Anyway, let me get the lights. And indeed it does last longer. So even with random defects, the dysprosium can trap their electrons and extend their lifetime. Tuning the lifetime is actually very important when you want phosphors for applications like cathode ray tubes. You want it long enough to produce a smooth flicker-free image, but fast enough that it can be redrawn without ghosting effects. Now I want to take a look at the dysprosium traps in more detail. I said before that the electrons in the conduction band fall into the dysprosium trap and eventually escape from the trap back into the conduction band. The question is, how are they getting the energy to escape? It has to come from somewhere. The answer is the dysprosium trap level is so close to the conduction band that thermal energy is enough to give the electrons that boost to escape. We can test this ourselves. I have here the same sample of strontium aluminate divided into 2 vials. And indeed, after hitting it with UV light, they both look the same and decay at the same rate since they're both at the same temperature. Now I'm heating the one on the left to 180 Celsius. And if we hit it with UV, we can see it decays very quickly compared to the room temperature sample. What's happening is the extra heating is helping electrons escape the dysprosium trap much faster. So the afterglow time is shortened. Now if I heat it up even higher to 300 Celsius, it barely even glows. The electrons jump out of the trap as soon as they get in. Forcing the trapped electrons out using heat is actually used in a scientific analysis technique called thermoluminescence dating. Remember how I said some minerals phosphoresce, but it's very weak? Well, some minerals also have trap defects that are too deep for the electrons to escape at room temperature. So they can remain trapped for years, centuries, or even millennia. And if carefully heated, they can be induced to emit light. This gives us a way to probe the history of a sample. But the effect is very weak, so you need sensitive equipment to detect it. Nonetheless, it exists. Okay, moving on. I said before that the Europium absorbs and emits light. The color of this emission is dependent on the energy difference between the ground state and the excited state. So if we can change that energy difference, we can change the color. The easiest way to do that is to change the material from strontium aluminate to calcium aluminate. We repeat the same procedure as strontium aluminate, but this time we substitute the strontium nitrate with calcium ammonium nitrate. We also decrease the dysprosium content from 2% down to 0.4% and increase the boric acid to 0.4 mole equivalents. Once we have that, we fire it in the microwave and there we go. Calcium aluminate phosphorescent powder, and this one gives a nice blue color. Although the quality of my sample isn't all that great, and despite testing lots of variations, I wasn't able to improve it. I think I need to purify my calcium nitrate further, but at least it works well enough for you to see. Now I said before I was using rare earth metals from Stanford Advanced Materials, but most amateurs can't buy from them since they're more oriented for businesses. So that leads to the question if rare earths from AliExpress or eBay could work. So I purchased some amateur accessible samples from AliExpress. I reacted those and produced these vials of metal nitrates. Under fluorescence, the europium seems fine. The dysprosium has sediment that didn't dissolve upon boiling in acid. I'm not sure what it was, but the solution still fluoresced just like dysprosium, so I tried anyway. And here is a batch of strontium aluminate doped with rare earths obtained from AliExpress. And it looks like it does work. Maybe very slightly less bright than the stuff from Stanford Advanced Materials, but I say good enough for amateur work. Of course, now we have to ask ourselves how the amateur-grade strontium and aluminum nitrates we made would compare to the professional stuff. So I went ahead and got some from Stanford Advanced Materials. This is the good stuff. Professional laboratory-grade strontium and aluminum nitrate. I mixed up a new batch, and here it is compared to the original made using amateur-grade strontium and aluminum nitrate. The high-quality stuff is a little brighter, but the real difference is the afterglow time. The professional grade material lasts much longer than the amateur grade. This is because the amateur stuff that we made has impurities that interfere with the trapped electrons and cause them to lose energy before they can emit light. The most common impurity is iron, just trace quantities can ruin phosphorescence. I'm time-lapsing this, but after 10 minutes my amateur grade stuff is long dead while the professional stuff is still absolutely demolishing. It's possible to bring our amateur grade material up to professional grade by repeat crystallization. But I'll be honest, after spending 4 months on this video, I didn't want to keep wasting time. I went through a lot of testing. It was awful, and I'm sorry this video was so late. Now at this point you may be asking if there are other colors we can make. They do exist, but they require different chemicals and processes. If there is strong interest, I may give them a try. Anyway, once you have samples you like, you can process them by separating out just the bits that glow and then removing the unreacted salts and urea by washing the powder in methanol and filtering. Then gently heating on the hot plate to dry them. Be careful you don't ignite the methanol. Afterward, you can grind the powder down to get a homogeneous mixture, but I prefer to leave them as flakes like this. So that was how we make glow-in-the-dark or phosphorescent powder. I hope that video was interesting. And let me know if you'd like me to try more colors with different chemicals, as well as ultra-purification of reagents to match professional grade materials. Also, special thanks to Stanford Advanced Materials for providing the metals for this experiment. Please subscribe, like, and share. And thank you for watching this whole video. It was absolute hell to make. I spent 4 months on it. I think I should have split it up into smaller lab notes and posted them as a series. Would you prefer that or as one big mega video like this? Anyway, if you could, please support me on Patreon. This video was tremendously costly in labor and time. Thanks a lot.